Hi, I'm Bena, and I'm going to be talking about natural language processing within a vector space. So the reason why we have ChatGPT and chatbots that help you when you're checking out an online order is because of natural language processing. And the goal of natural language processing is to be able to talk to a computer and talk to it in English or any other language, and for it to understand you and be able to formulate what you're saying into code or a language that the computer understands. So the way that we do this is by finding associated and related words and words that have relationships with each other or similar meanings. So this is the procedure for doing that. This is one of the many procedures for finding correlations between words. This is the TF minus IDF procedure. So we see that this first table here, table one, we have three documents, document one, document two, and document three. And we're looking for the relationship between the words good, car, and mechanic. So we go through each document and we count how many times these words appear in these documents. So good appeared once in document one and 0 times in document three. So then we're going to transform these numbers using the TF minus IDF formula. And the reason for doing this is because it reduces the importance of words that appear frequently in all documents. So words like a and the, right, they're going to be associated with every word on earth, right? Because they're used so frequently in every single document. So we penalize those words. And we really focus on the rare words because the thinking is that those words are going to be more important and tell us more about the meaning behind the document. So after this transform, we get this matrix on the right. And then we can map this into vector space like we see here on the bottom. So this D1 vector represents document one, and you can see it has a large association, this 9.1 value with good, but not so much with mechanic, and not at all with car, right? Because those vectors are 0. And we can see the same for D2 and D3, no association with car at all, but a little with the others, and a lot for mechanic for D3. All right, so then when we want to look at higher dimensions, so more than 3 words, it becomes a little bit more complicated. When we do this in higher dimensions, every word is an axis, right? So now we have 3 axes, 3 words. But imagine what that would look like with 3 million words, right? So it gets a little more complicated. And every document that we have is going to be a vector of associations between words. So document one, document two, et cetera, et cetera. And we call these documents, this collection of documents that we use to train our model, we call that a corpus. So that's our corpus for training our model. So an example of a corpus being made is the Google News a corpus being used is the Google News corpus, which was created using the Google Word2Vec tool. And Google Word2Vec doesn't use the TF-IDF procedure. It uses a different procedure to calculate these correlations between words. So this example on the right is an example where someone typed in France, and these are all the correlations between France and those words. Google Word2Vec uses the cosine distances between these vectors to find these correlations between words. So here's an example in R, and we're going to be using the Brown package as our corpus, and we can investigate the Brown package a little bit more. It has 5,000 or 57,000 words or sentences. So then we can get these sentences into an object, and we can use them to train our model. So here's where we train our model. And then we have to make these words, although like Word2Vec does some processing, it puts them into an object and we have to extract the vector. So here's where we're extracting the vectors. And then when we can look up a certain word like computer, we can print that word vector. So here's the word vector for computer. So every one of these, and the algorithm is going to be different from the TF minus IDF procedure. So that's why these vectors might look different than one might expect in the TF IDF procedure. But there's some sort of transformation here that will allow them to calculate distances between words. So then when we go and we want to find those most similar words, we use this command, most similar, and we type in computer again. And we get these words here: camera, fortunes, etc. And pretty much what these are words that are closest to computer within the vector space. And so these words might look a little weird, right? Pork, like these don't really make a lot of sense. But keep in mind that our corpus was relatively small, right? 57,000 sentences is not going to have every word in the English dictionary, right? So then we can do some more analysis and find words that don't match within this array. So cheese was the one that didn't match. Then we can make a PCA, but we're going to talk about that a little bit first. So the goal of principal component analysis is to reduce dimensionality. And so the reason we want to do this is because, remember, we have like thousands of axes, right? So we want to translate a complicated vector space into a one-dimensional graph so we can view these relationships more clearly. So the way we do PCA is first find PC1, our x-axis, which is going to be the direction that has that highest variance. So the data points are more spread out, and that's going to be most interesting to us. Because we don't really care about the other direction where all the points are going to be relatively similar. So we choose the direction with the highest variance. And then to choose PC2, we're going to choose the second highest variance, but that's going to be orthogonal to PC1, right? So we see this orthogonal vector here being used to transform this data into a one-dimensional space. So then on the right here, we can see an example of when this is done for this word vector space. We can see similar words that are really close together, and not so similar words like Berlin and similar aren't going to be very close. All right, so now we're going to create our PCA in R. So here's the formula for doing so. This is creating the plot, etc. And then we're going to send in our model, and we have to send in the vectors of the model. And we're going to send in the words that we want to compare. So then we get this graph here, this PCA, and we can see coffee, wine, and beer are close, college and university are close, and there's some like weirdness going on, right? College and school should probably be closer, but remember that it all matters upon what we're training our data set upon. So we need to use more words and more resources if we want our relationships to be very accurate. So now we can look at how we can translate these vector spaces and these relationships to making predictions about objects. So we can see that in different vector spaces, similar relationships exist between objects that have similar relationships. So king and queen are going to have a similar relationship to man and woman, and that's seen by our similarities in our vector spaces. Same in word to vec, right? So if we mapped all of the ing verbs, those are going to have an association with the present or past tense verbs, right? Just because of the location of the vectors. Now we can talk about the uses of NLP. So the first is going to be translation services. So we can see these relationships here, and we can kind of imagine what this would look like if we mapped two different languages vector space. So if we were to map English as a vector space and Spanish as a vector space, we might see something like hello is to goodbye as hola is to adios, right? So we can kind of make the assumption that all of these words are going to have similar meanings. If we know maybe three of them and we want to know the related fourth word, right? That can help us do so. Similarly, sentiment analysis, we can come up with which words are going to be similar. So like in this PCA here, we see that poor, awful, and terrible are words with bad sentiment, and they're all clumped together because they have similar meaning, and they're used in a similar way in documents. So we can use those those assumptions that those words are going to be similar to extrapolate meaning from a lot of different words that have similar meanings. So that can be used for social media monitoring. If someone is using a hateful speech or doing something harmful on the internet, sentiment analysis or common words and phrases that are found in these damaging posts can be monitored and removed. We can also use natural language processing for email filtering. So determining which words are common in a spam email and filtering them out, filtering spam emails out. Also, automatic summarization. So coming up with easier ways to say things, more simple ways of saying things. That all relates to being able to derive the meaning from a lot of different words. And that's what natural language processing allows us to do. And I like this quote: natural language processing makes it possible for humans to talk to machines. And that's really the end goal of natural language processing, is to be able to speak to a machine in English or Spanish or whatever language you want. And the machine will be able to understand you, and you don't have to code up what you want it to do. You can just tell it verbally. So we need to be aware of the bias that exists in natural language process models. So in this example, we want to evaluate the relationship between king and queen and man and woman. So say we know the relationship between man and woman, and we want to know what is the equivalent to woman as king is to man. So we do this vector arithmetic and we get these new vectors, this new vector queen. So even here in this model, right, king and queen being related to man and woman, like already it's kind of going out of fashion, right? We have other genders other than man and woman that might be associated with king or queen. And there might be, maybe not man or woman at all. Like, what's the association with someone else, right? So we need to really be careful when we're training our natural language processing models. So if you train your model with a corpus that's small and relates to one community, it's going to be lacking for the other communities, right? We're going to perpetuate historical biases if we continue to train our models on historical data, right? These natural language processing models can only make relationships based on what we give it. So we need to be really aware of how we're training our model, and we need to include a wide breadth of resources to train our model. I hope you enjoyed the presentation. Thank you very much.